In part 2 of function transformations, we're going to look at 3 more sets of transformation types. In set 3, we're going to look at the transformations using a negative, and you can see that f is going to be negative x squared and g is negative x in parentheses squared. And you might wonder, well, does that make a difference? But by exploring, you can find out if in fact it does make a difference. So as you can see, I already have these equations in my y equals. I have the x squared and the negative x squared in blue and the negative x in parentheses squared here. I want to complete this table for the values that are given me, so I'm going to go to second table. This is the one for x squared, and I can see it if I scroll over here. If I go up here, it'll show me that I'm doing y equals x squared in y1. If I go over to y2, I'm doing y equals negative x squared, and my y3 is negative x in parentheses squared, and I have my values that I need to complete this table. So let's pause here while we complete the table. And we're back. So by observing the output values, these dependent values, these y values, the f of x values, whatever you want to call them, you can see that in fact the negative x squared does make a difference when we're comparing it to the negative x and then squared. Because once we have in the first we would square it and then we would take the opposite. In the second, first we would take the opposite and then we would square it. And we should know that when we square something, whether we're multiplying positive times positive or negative times negative, we're always going to get a positive. So the next thing we want to do is look and see what this does to our parent function. And if you recall, the parent function here in the basic black is f of x equals x squared. And we've graphed this here just to sketch to see what happens to these other functions. Since the first function has negative 2, negative 4, we're going to put a point there. And it has a negative 1, negative 1. And it has a 0, 0. And it has a 1, negative 1. And a 2, negative 4. And so I want to sketch that function, sketch that parabola as it is given there. Then I have the negative x squared. Well, negative x squared has the negative 2, 4, the negative 1, 1, 0, 0, 1, 1, and 2, 4. And so I sketch it. And it has been supposedly transformed. It doesn't look to me like much has changed. So when we look at what has changed, what do we notice? Well, what you should notice is that if you do have this negative on the outside of the x, it's on the outside of the x, what it's doing is it's changing every value of y. It's taking every positive y that you have here in black and green, and it is reflecting it across the x-axis and making it negative. So when we say what is the change here in negative x squared, we could say that it flips. That's what people are going to say, is that the parabola flips. The mathematical term for that is that it reflects across the x-axis. And if I imagine that this x-axis, which it is, here it's going across here, this x-axis is reflective material, then the graph above the axis has now reflected below the axis, and every positive y is now a negative y. All the x's stay the same, just like they always do. That's why they're your x's. Now, with g, we have negative x inside the parentheses. We thought x changed, but did it really? We thought it changed, but then we squared it again because that's just the function. That's how it works. Thought you changed x, and you square it again, and it comes right back out, and it's just the same. This is the same as the original function. They both have the same shape. The negative x squared in blue has been reflected across the x-axis, and inside the parentheses, raised to the second power is the same. Now, something that you're going to notice, and it's not on this form or anything like that, is that you're going to notice as you go through and you're looking at different functions, the exponent is going to make a difference in what happens as you reflect across the x-axis. If they're even, you're going to see this kind of phenomenon happen, like if it's to the 4th or to the 6th. But if it's odd, you're going to see something else happen, because a negative times a negative times a negative is not the same as a positive times a positive times a positive. So you'll see that happen as you explore other functions. And now we'll go to set 4. In set 4, we're looking at what happens if I multiply the parent function, f of x equals x squared. What happens if I multiply that by a number like 2, a number that's larger than 1? What happens if I multiply that function by a fraction that is between this number, that is between, let's call it c, and we say that it is between 1 and 0. It's not 0. It's not 1. It's between 1 and 0. It's a fraction that has a value that's less than 1 but greater than 0. Let's do exactly what we did with set 3 in your calculator and finish up set 4. For our 1/2 x squared function at -2, we will have 2, because it's 1/2 of -2 squared. At -1, we'll have 1/2. At 0, we'll have 0. At 1, we will have 1/2. Or 0.5. You probably see 0.5 in your calculator. And at 2, we have 2. So you have to recall what you saw with x squared. With the function x squared, these same x values, we had x is -2, 1, 0, 1, 2. We had our y's equal 4, 1, 0, 1, 4. And that's what you see graphed there in the basic black. So with the 2x squared, I want to graph my function. I have -2, 8. So go over here to -2 and up here to 8. And 1 or -1, 2 and 0, 0. And 1, 2 and 2, 8. Notice the symmetry again. You can see the equidistant from the y-axis, because this has symmetry with the y-axis. You can see that equidistance from here to here from the y-axis to each of those points. So make our little sketch of the 2x squared and put our little arrows on the end. For the 1/2 x squared, we have -2, 2. We have -1, 1/2. And we have to estimate that, but it's close enough. It's a sketch. We have 1, 1/2 and 2, 2. Now, I might want to look at my table and get a couple of other values just so I can get a better shape. So if I go to x is 3, I'll see that I get 4.5, and that's going to be about there. And if I go to -3, I'll get 4.5 about here. And I could do the 4. If I go with the 4, then I'm going to get 8. And then another -4 and the 8. And so I sketch that parabola. I know I'm off, but the point is there to remind me if I really want to, I can erase and make sure it's going through that point that I want. But again, these are just sketches to give us an idea of what we're seeing here in the tables to give us a visualization. So with the 2x squared, what does it look like happened? Well, if you compare the width of the function, the width of the graph, the 2x squared looks narrower. So you could say that it was more narrow. If you imagine that there are, on the ends of these arrows, if we were to pull those arrows up, both of them at the same time, with the same force on them, if we pulled those up and stretched this graph, we could make it go to that blue spot. So we could say that it's stretched. And in fact, it's stretched by a factor of 2. Because that 2 meant something. If I had a 3 there, it'd be stretched by a factor of 3. And you can even look at this, it's going to get more narrow. And 4x squared would be even more narrow by a factor of 4. Has it really changed its position? No, because it's like this anchor. The anchor, the vertex, is still there in the same spot. There's no reflection. There's no movement. It's a stretch. Or in the case of the 1/2, where the number is between 0 and 1, then we have it's wider. The graph is wider. It has been compressed. Compressed by a factor of 2. So we see that that's what happens, and what we're doing here is demonstrating that this is going to happen, and when you take some other parent function, the same thing is going to happen there. So let's go to our set 5. In set 5, we are multiplying again, but notice the difference. Here, I have no parentheses. I'm multiplying each y value. Each y value was multiplied by 2. So this was f of x. Well, now it's 2 times f of x. That's where that would come from. If f of x was the original function, 2 times the parent function, and 1/2 times the parent function for the other side. But what's happening over here is that what is happening to the function is just happening to x. So these parentheses are going to make things look a little bit different. So take a minute to put those in your calculator and come back to the video when you have that in the table, those values in the table. So we come back from our table and our 2x squared function, where we've multiplied each value of x by 2 and then squared it. For -2, we have 16, which is 2, 4, 6, 8, 10, 12, 14, somewhere up here. And we have the same thing happening over here. Just somewhere up here we're estimating. And at -1, we're at 4. At 1, we're at 4. And at 0, we're at 4. I mean, at 0, we're at 0. So again, let me do that sketch. We don't even have to go that far if we don't want to, because that looks kind of messy. We have a goal up there that's where we're going to get to. So we're just going to leave it like this. The 1/2, x has been compressed or made smaller, and then we square it. So at -2, we're at 1, and at 2, we're at 1. See that symmetry happening. At -1, we're at 1/4. Really close down here. And at 1, we're at 1/4. And at 2, oh, we've already done it. At 3, maybe we want to go to the 4, and at the 4 we'll have, we'll be at 4. Have a little bit more to give us a good sketch. And look at what's happened here. So again, we see multiplying by 2 inside. When you multiply by 2 or a number that's greater than 1 inside the parentheses, then we're more narrow. And when we could also say that was, this is a horizontal thing. This is happening horizontally because it's inside the parentheses. So we're going to call that a horizontal compression. Notice we're using different terms now. Because it happened inside the parentheses, and by it happened inside the parentheses, when we have an inside, we do something to the x value, and so these x values have been smooshed together, in other words, compressed, because compression sounds a whole lot more educational than smooshed. With the green, then we have a wider function, and we have a horizontal stretch, because we are pulling those horizontal points away from their parent position. And these are just some different terms that you'll see used. You'll see them change around. You got to just be able to put it together and interpret it properly. So those are what we see with our horizontal compression and stretches. Then we have our vertical compressions and stretches. And we have our reflections across the x-axis. So that's all I have for part 2 of transformations. This is all that I have to say about that.